Okay, so last time we finished up, I think we got through Einstein, but we didn't do Debye, right? And so Einstein had made some assumptions. The one that sort of helped things out, or going back to the original problem, is DeLong and Petit said that the heat capacity, and we did the derivation for it, that the heat capacity should be 3R for anything. So this right here, line here would be the 3R. At low temperatures, what we see experimentally is that the heat capacity, and that's the circular data points, heat capacity starts dropping down, and if you get close to 0 Kelvin, the heat capacity drops to 0, right? So Einstein used Planck's idea that energy was quantized, and then we apply that, so we replace the there we go. Classic physics, which was energy is equal to kBT with, or energy is equal, and this is just rehashing what we had before, right? Should be, 1/2 kBT with 1/2 h nu over e to the h nu divided by kBT minus 1. Right? So Einstein replaced or changed using the average energy, which was the classical value, with energy, and this is the Debye sign, with average energy that we get if we assume quantized states, right? Now Einstein's assumption in this derivation, or in the derivation that we did, was that all the atoms have the exact same frequency of oscillation, right? And so if we look at the value, Einstein's gives the general shape fairly well, that's the red line here, right? But it doesn't quite fit. So what Debye did, and we're not going to do the actual full derivation, because in order to solve it, you actually have to use a computer to solve it numerically, right? So, but what Debye did was he dropped the assumption that all the frequencies are the same, right? So now you have to integrate over your various frequencies, and he came up with the heat capacity, the molar heat capacity, is equal to 3RF, where F is equal to 3 your temperature over Debye temperature, and this is in your book, 3 integral 0 okay. The key point there is the end result is similar to Einstein's, but this one has an integral one, right? The previous one up here looked fairly similar, but it wasn't integrating over all your frequencies. This one does, and if you include that extra bit of work, we find that the Debye's heat capacity matches up with the experimental really, really, really well, right? So again, that's going to deriving your equations, or the assumptions that you're putting into the equations dictate the equation you get out at the end. Einstein did a fairly decent job of coming up with a model to predict the behavior, but oversimplified it a little bit too much, and that's why the predicted results from his equation don't really match up with the experiment. I mean, it tracks fairly well, but you need to add that little bit of complexity to get the actual number. But depending on the level of accuracy that you need, right, doing that oversimplification where all the frequencies are the same might get you good enough results. Right? So that's one of the things through all these derivations that we're going to be doing. The question is, what's good enough, right? Okay. Now, again, I don't expect you to be able to do the full derivations on a homework or test, or apply the values you get out at the end. Yeah?
Just a question about the device
Mhm.
calculation for heat capacity. So heat capacity was 3RF, where F is the various frequencies.
F is a function,
F is a function.
and this here is the function.
And R stands for constant.
R is the gas constant. Yeah. Okay, now, so Einstein, with his heat capacity, had shown that this idea of quantized states or energy being quantized doesn't apply to just photons and electrons. When we were doing the derivation for Einstein's heat capacity, he was using it for any atom, right? So it's applying to a full atom, not the subatomic particles, right? So de Broglie went along those same lines and proposed that all particles have a wavelength, right? So everything has a wavelength that is related to their momentum. So the symbol that gets used for momentum looks a lot like a P, but it's actually rho, right? So we're going to use this today. Rho, that is your momentum. Okay? And from physics, momentum is mass times velocity. Now, he proposed, de Broglie proposed that your momentum was equal to Planck's constant divided by the wavelength. Or you could re-express it as the wavelength is Planck's constant divided by your momentum, depending on what you're interested in, right? So, using electron beams being fired at a crystal gives a diffraction pattern that's consistent with this de Broglie idea. Essentially, you might have seen these crystal diffraction patterns. It's one of the ways that they figure out the structure of a crystalline object, right? It's used in proteins. More historically, it was used to figure out the crystal structure of things like sodium chloride, iron oxide, all your different crystal structures. This is how they figured out what they look like. So essentially you have, let's say you have a simple cubic, right? Your light comes in, and depending on, so if this is your nucleus, these are the atoms. The structure itself, as the electrons are being fired through, if their wavelength is similar to, or is on a similar magnitude to the difference between the distance of the two nuclei, you get a diffraction pattern, right? So similar to what we were talking about earlier, where you have, you know, the dual slit experiment, and you have the interferogram. So a dark spot, light spot, dark, light, going down, right? You see the same thing if you fire a beam of electrons at a crystal, except instead of being along a line, it's in more on a plane, so a two-dimensional surface. So what you end up seeing is you're firing it through sort of a grating. You can think of the crystal structure as being a grating. So you have the center, which is the electrons passing through undiffracted, right? And then what you see is instead of having lines, you have circles, right? of light, dark, light, dark. These circles are actually, you know, more filled in. Right, so if you Google diffraction pattern, you'll see a whole bunch of these circles, and some of them have different shapes. So you might have not a perfect circle, but dots arranged in different quadrants, and you can back calculate, or people have back calculated what the crystal structure looks like based on these diffraction patterns. Right? So this is how we actually figure out what crystals look like, is using this concept of de Broglie's wavelength for an electron. If you get it going with a certain amount of energy, right, or moving with a particular momentum, then you know, you can set the wavelength as long as the wavelength is similar to the distance between the atoms. So on the sort of angstrom-esque order, you end up getting these diffraction patterns. Okay? Now, everything actually has a wavelength. So all particles have a wavelength, that chair has a wavelength, right? But it's dependent on the momentum. Mass times velocity is equal to Planck's constant over wavelength. So if you think the mass of a chair, right, is a couple kilograms, that's, you know, 1 times 10 to the first-ish power, times the velocity. Well, it's not really moving all that fast, but I guess if you take into account, you know, the motion of the Earth, it has some velocity. Planck's constant is a really small number, 6.626 times 10 to the negative 34. Right? So if you have something that is 1 times 10 to the first, right, times some velocity, right? It doesn't have to be all that fast. That's equal to 6.626 times 10 to the negative 34, right, over wavelength. If this is something on the order of whatever velocity it's moving at, you can see that this wavelength, in order to get you back onto this size of magnitude, the wavelength has to be really, really small. Right? So for everyday objects, because they are really, really massive, they don't have much of a wavelength. In fact, most of the time the wavelength is on this order of, you know, times 10 to the negative 34, really, really small. So you don't actually perceive it because the wavelength is so small. But if we're talking about like an electron, electrons have a mass of, what is it, times 10 to the negative 11th kilograms, somewhere around there. So if this is times 10 to the negative 11th, then, and is moving at, you know, less than the speed of light, this is a fairly small number, and so the wavelength doesn't have to be all that long, right? So for objects that are really small, the wavelength, the wave-like nature becomes important. And photons have really, really low, instead of having an actual mass, they have a momentum, right? So the h nu is their momentum, and from that you can find the wavelength, okay? Now the key when you're doing one of these calculations is keeping track of your units, right? So the mass needs to be in kilograms, and the velocity should be in meters per second, right? And that's because you need all your units to cancel out. The unit for Planck's constant is joule seconds, right? And so you need your velocity to be in something per second. Wavelength, most of the time, is going to be in units of meters. Could be picometers, could be millimeters, right? But as long as you go to the base unit, convert everything to the base unit, then things will cancel out the way you want them to. Right? So your, because the unit for H is joule seconds, joules is a kilogram meter per second squared. And so you need the mass unit, the kilograms, to match up with the joule kilogram so they'll cancel each other out. Okay, that's one of the most common mistakes, is not keeping track of your units. So for this class, more than any other of your classes that you've had, units are going to be critical, right? If you put the units in it's a good way to check, and we're going to do some of that today. Check to make sure that our calculation looks right, just by looking at, do the units agree with what that we think they should be. It's a good check to see if in your derivation you made a mistake. If your units don't work out, then chances are you dropped a square or put in a wrong negative sign somewhere. It all works out if you keep track of the units. Okay? So one of the things that we'd be interested in is what is the wavelength of a particular object given a mass and a velocity. And we'll have a problem several slides down where we're actually going to practice that. Okay? Now, a little bit more evidence for quantum mechanics, emission spectra, right? So if energy was not quantized, then what you would expect is black body radiation, right? So a continuous spectra coming out from everything. But what we see is that the hydrogen, one of the easiest ones to do, the hydrogen absorption or emission spectra, depending on what you're doing, has these bands of bright lights. So this would be the emission spectra. If you take a hydrogen lamp, pass an arc of voltage through it, right, you get the light. You probably have done that in like Gen Chem, where they had the little viewers and you worked out what the wavelengths were. Okay, so all atoms have a different emission spectra. You can look them up. This is one of the ways that we figure out the concentration of metal contaminants in like water samples, right? So if you want to know how much lead is in your water sample, you run it through an atomic absorption spectrometer. We have one in the other room. Essentially what it does is it aspirates the liquid into a flame. That flame excites all the electrons up, they relax back down, and they give off energy. And you can look at the particular wavelengths that correspond to that metal. So what it typically has is you have whatever you're interested in, you have a lamp that's shining that light, which should excite the atoms, and then you measure the difference in the intensity of the light. Right? So that's how we can figure out, the lead content really, really accurately of samples, right? Or, hydrogen or helium or neon, sodium in a particular sample. We use an atomic emission spectra. Another one is if you have your regular absorption spectra, you might have noticed that it has the wavy parts here. That's not actually noise, that is an effect of quantum mechanics. Right? Well, some of it might be noise, but no matter how clean you can get it, how strong your signal is going to be, you're going to have some of that waviness, which is based on quantized states. Okay, so going back to our concept of these spectra, right? For a long time, chemists knew that atoms, when heated up, or when you put an electric charge through them, they gave a particular electromagnetic radiation in discrete frequencies. And that is here, that's your emission spectra. So a hydrogen lamp will give very discrete frequencies. The way they figured that out, they had these lamps, pass them through a prism that separates them out, and what you'd see on your back wall are these vertical colored lines. Right? So they were doing this about the time that they came up with reproducible ways of making electricity. Right? So once you have an electric source, then you can put a shock through, like static electricity through, and if you have just hydrogen gas, you just have it pure hydrogen gas, no oxygen, right? You can see an emission spectrum. Right? So the first series that were looked at was the hydrogen atom. Right? It was the lightest one, so they thought it was the most basic atom. So Balmer was one of the first people that found a relationship, found that the hydrogen spectra, or at least some of the lines, called the Balmer series. So it came up with a mathematical expression for the distance between a particular set of lines, followed this particular equation, where the frequency of those lines was equal to this constant times 1 minus 4 divided by n, some integer value, raised to the second power of hertz. Make a little bit of room. Now, if you remember from general chemistry, we had the Rydberg equation, right, which we use to describe energy absorbed or emitted from the hydrogen atom, which is essentially 1 over your wavelength is equal to the Rydberg constant, 1 over n 1 squared minus 1 over n 2 squared. All right. Hopefully you remember from Gen Chem. Yes? Okay. If you look at this equation, if we take what's in here, divided it by 4, you'd get your frequency. And just as a reminder, you know, your speed of light is equal to frequency times your wavelength. So your frequency is equal to the speed of light divided by your wavelength. So they're proportional to each other. So if we say our frequency is equal to some constant, which in this case they're using 8.22 times 10 to the 14, right? Some constant, doesn't really matter what it is. If we divide what's in the parentheses by 4, we get 1 over 4 minus 1 over n squared, right? And this 4 is 2 squared, right? So 4 is equal to 2 squared. So essentially, what the Balmer series is all the values that we eventually get for the Rydberg equation, where n1 is starting out at the second energy level. So getting excited from 2 to 3, 2 to 4, 2 to 5, 2 to 6, that's the Balmer series, right? So this part here, where it's raised to the 4th power, making this 1, if we divide everything by 4, we get 1/4, which is 1 over 2 squared, right? So Balmer was the first one to come up with this series. A bunch of other people came up with similar ones, and then it was Rydberg who put them all together into this overall equation. All right, so some of the other ones were, brain can't remember the names, but they're dead, so they don't care. 1 over 1 to the various ends, that was one series, 1 over 3. So you had three or four different people who came up with a similar equation where it was, 1 over n to some value, or some value minus 1 over n squared. And then the various n's were 1, 3, and 9 for hydrogen, right? And it was Balmer who realized that value here, that is a different n squared. This predates Planck's idea of quantized states. It was just the math works out to have these quantized values. No one actually thought from those quantized values we have quantized energies. It was just these lines that we know exist experimentally fit this equation, right? But there wasn't an explanation for why the heck this was, nor was there an explanation for why the Rydberg constant, the numerical value for it, is the way it is. It's just, this is what the math works out to be. So it would be pretty cool, at least, I don't know, from a geeky perspective, if we had a model that reproduced that and came up with the Rydberg value. So if you remember Bohr, took, what was it, Thomson's or Kelvin's idea of an atom with a circular, an atom being the nucleus in the middle with the electrons orbiting in planet-like motion. All right, so you have the nucleus, which has by far the majority of the mass, and then you have an electron, which is going around and around, right? And if we're talking about a hydrogen atom, the charge on the nucleus is the same but in the opposite sign as the charge on the electron, right? So if we use this idea, this model, we have a nucleus with a particular mass, an electron with a particular mass, the electron's moving around, it would be really cool if we could derive that, right? And it was Bohr who was using the idea of quantized energy states in his model, right? So the reason that the electron doesn't crash into the center is because where it's located is based on a quantized energy state, right? It can't actually degrade because the value is stuck at a particular number. Now, if we're using this model, we're going to make a couple assumptions, right? The nucleus has the vast majority of the mass, right? So to a good extent, the motion of the electron has no real big impact on where the nucleus is at. So we're going to assume that the nucleus doesn't move. Okay? And that the charge of the protons is equal to the charge of the electrons. And I'm going to use, so I think your book uses C or E. It's either C or E for the charge on the electron. I'm going to use a C sub E. I think using E for charge is confusing because we already have E raised to a power, right? And in this derivation, we're going to end up with an E squared. Or well, if we used E to represent the charge on an electron, it would look like E squared, but it's actually the charge squared, right? So I'm going to be using CE for charge on electron. Okay, so before we do this derivation, I want to write up some of the symbols.
Would it be negative?
They're opposite in sign, but it's when we're going to be using the Coulombic force, and so it's the absolute value of the magnitude multiplied together. So yes, the charge on a proton is the negative of it, but because it's using the Coulombic force, it's the absolute value of them multiplied together. So the negative sign isn't really going to matter. Okay, so I want to write up some of the symbols that we're going to be using, just so we have them over here. So when you see them on the equation, they sort of make sense, right? Okay, so this is our model. This is our goal. We have rho, which is the linear momentum. And linear momentum is equal to mass times velocity. Okay, we have m, which is our mass, v, which is going to be velocity, we have nu, I'm going to use nu ROT, and this will be the rotational frequency. Essentially, how often per unit time does the electron make it around the circle? Right. So the frequency of going around the orbit is going to be our rotational frequency. Okay. Omega ROT. This is the angular angular velocity. So this will be 2 pi times inertia. Which is equal to m over r squared. And then L, and I'll try to make my L look like that.
Wait, M over or M R squared?
Hmm?
M over R squared?
No, m times r squared. So I is equal to m times r squared. This, that's gonna be, you're gonna use that for L. That way my L's don't look like ones. That's the angular momentum. Okay. So, what we're going to do is we're going to first try to figure out how far that electron is out. Right, so essentially for a hydrogen atom, how far is that electron from the nuclei, from the nucleus, right? Okay. So the kinetic energy that you're probably more familiar with is the 1/2 m v squared, right? So that is the amount of energy that this electron has. If we forget that it's moving around a circle, if we just look tangentially, it's moving with a particular velocity, it has a mass, so it has kinetic energy. But it's not moving linearly, it's moving around in a circle. So instead of talking about the linear kinetic energy, we need to figure out what the rotational kinetic energy is, right? But I want to ground this in something that you're hopefully familiar with. Is my writing over here large enough for you to see? Big enough? Okay. So if we look at it in terms of rotational, this would be 1/2 times the velocity is the radius times our was that our angular velocity, right? So how far out it is times how fast it's moving in terms of radians, right? So this part here, r times omega, that is our velocity. We have velocity squared, so we need to have that be squared. Right, so this is, drop my mass, r omega squared. Okay, so we can distribute that out. This is 1/2 m r squared omega squared. This is equal to 1/2 our moment of inertia times our angular velocity. All right, so you can sort of see, if we compare this here with this, our mass is sort of analogous to our rotational inertia, and our velocity is analogous to our angular velocity. Okay, so our angular momentum should be somewhat similar to our linear momentum, right? Except instead of using m and b, we're going to use our moment of inertia and our angular velocity. So it is I omega. Which would be mass times r squared v over r, where r R's cancel out, right? So MV, yeah, so your R's cancel out, this would be M, V, R. Right, the difference is how far out it is gives you your rotational, or sorry, your angular momentum versus your linear momentum. Right, so you need to have that rotational component in there. Okay. So our kinetic energy, so if we're looking at a linear system, our kinetic energy is equal to 1/2 mv squared, or mv squared over 2. Our momentum, right, is m times v. So you can actually rewrite this as m times v squared over 2m. Right. The difference here is if we take mv squared, we get m squared v squared, but we're dividing by m, so we get back that equation. Now mv is our linear momentum, so we could write this out as our linear momentum squared divided by 2 times our mass. For a rotating system, kinetic energy is going to be very similar, except where we have an m, we're going to use an I, and where we have a v, it's our omega, right? So it's I omega squared over 2, which would be, we could re-represent this as I omega squared over 2I, or we could use our angular momentum squared divided by 2I. Okay. So if we have something that is moving around, going in an elliptical orbit or planetary type motion, there has to be a force to balance out or to pull it in that balances out the tendency to go out, right? So you have the centrifugal force, which is pushing it out. We have to have a force that's matching it, pulling it in, right? Otherwise it would fly out. So the force, the centrifugal force, F, is going to be mv squared over r. Right? That's sort of your centrifugal force. The force that's holding it in, if we think about our concept of an atom, right, we have a positively charged nucleus, negatively charged electron. What's holding the electron in place is the attractive force between the electron and the proton, right? And so because it's a charge-charge interaction, that's a Coulombic force. So I'm going to use, so this is our centrifugal. Right, that's force pushing it out. Our force pulling it in, I'm going to use F sub C for force Coulombic. So the Coulombic force is the charge, absolute value of the charge of the proton, times the charge on the electron, divided by 4 pi. That E-looking thing is our permissivity, how well the charge goes through, in this case, free space, times the R squared. So let me just add that. This symbol here is permissivity. is equal, that's just a constant, that's 8.85419 times 10 to the negative 12th. Units are coulombs squared, Newton to the negative 1, meters to the negative 2. Oh, and because over here, right, we had our centrifugal force, and we're talking about the electron being the thing that's moving around, the mass that we're going to be working with is the mass of the electron, which is 9.110 times 10 to the negative 31 kilograms. And then the charge on the electron is 1.602 times 10 to the minus 19th coulombs. Okay, those are just constants that we're going to plug in a bit. But, yeah. Okay, so instead of using the charge on the proton, charge on the electron, we're going to just use C sub E. You got the absolute value, so the fact that they have different signs doesn't matter. And because they're the exact same number, we're just going to use the charge on the electron squared over 4 pi E naught R squared. Okay, so the force for the electron moving out has to be balanced with the force pulling it in to keep it in the orbit. Right, so this value here, the centrifugal, has to match the coulombic. So, that means that C E squared 4 pi E not R squared has to equal the mass of the electron times the velocity over R. Squared for the velocity. Okay, so Bohr's key is that energy is quantized, right? So that means that our kinetic energy is quantized, or sorry, our angular momentum is quantized, which is related to the kinetic energy, so that would also be quantized. But what we're going to do is we're going to say that our angular momentum is equal, or which is equal to the mass of the electron times the velocity times the radius, is equal to NH bar. Now the H bar is something that we're going to use a lot. So H bar is equal to Planck's constant over 2 pi. And this is called H bar. The reason why we have its own constant with a funky symbol is because a lot of the times we're using sine type waves, and so the 2 pi creeps in there a whole lot. Right? And so it's just convenient, instead of having to write h over 2 pi a whole bunch of times, to just have h bar. It's something to be aware of. Now, so this is for, we're saying that it's quantized, so that's for n equaling 1, 2, 3, dot, 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 quantized state. We could plug a 0 in, but if you plug a 0 in for n, that's 0, and so we're talking about a state that has no energy. Right? So it doesn't really, it would be an electron that really isn't anywhere. So we're starting off with n equals 1. Okay, so if we're interested in finding the radius, one of the things we can do, solve for velocity, which will eventually enable us to get radius. Right, we're going to use the velocity, plugging it back in here to get it in terms of radius. Right, so essentially we have an equation here, we got two unknowns, radius and velocity. If we can express velocity in terms of radius, we can plug it back in here, and then we get rid of all of our unknowns except radius, solve for radius, and we get our answer. Okay? So, solving this for velocity would be moving the mass of the electron and the radius to the other side. So our velocity is equal to n h bar over mass of the electron times the radius. We can then take that, plug it in here to get rid of one of our unknowns, our velocity. So that gives us the charge of an electron squared over 4 pi, our permittivity, r squared, is equal to the mass of an electron over r, and then plug this in for velocity, so that would be n h bar over mass of an electron r. Here was velocity squared, and so what's in the parentheses needs to be squared. Okay, so this side here, we have a bunch of different terms. We can simplify this a little bit, bring our r's together and our m sub e's. So this is equal to n squared h bar squared over negative, see here you have m in the numerator times 1 over m mass of the electron squared, where that's in the denominator. And so this is going to cancel out one of those, but we'll still have one left over. So mass of the electron, this is essentially 1 over r squared. That's in the denominator, so it'll come down here, giving us r to the third power. Okay, we want to solve for r. If you look here, we got r squared on the left, r to the third on the right. We can cross some of that out. Right? So the r squared here will cancel out all but one of those r's. Move r to the left, everything else to the right. So we're going to solve for our r. That would give us r is equal to move the 4 pi e naught to the right, so that would be 4 pi e naught n squared, I'm going to keep h bar squared over mass of the electron times the charge of the electron squared. Now, it might look like a fairly complicated equation, but we know all those numbers. Well, we know all the numbers but n, and n just depends on which particular state, which energy level we want to do. Right? So constant, 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 constant. Then we just vary n to say the first orbit is at this distance, the second one's at that, third one's at this, and so that's how we figure out our distances. So let's plug in 1 for n and figure out for a ground state hydrogen atom just how wide it should be. So that is 4 pi. I'm going to check parentheses around our constants just so you can see where what the numbers are. Right? So this is 8.85419 times 10 to the minus 12th coulombs, newtons to the -1, meters to the -2. Okay, that's our permittivity. Oh, yes, bonus point. Coulomb squared. N, we're trying 1, right? We're looking here, the next value is n. 1 squared is 1, and so times 1, times 1 squared times, and the n is unitless, right? Our energy level itself is either the first, second, third. There's no units on it. H bar is Planck's constant divided by 2m, Planck's constant divided by 2 pi, so it'll have the same units as Planck's constant. So that works out to be 1.055 times 10 to the minus 34 joules times seconds, and that value is squared. That whole thing gets divided by the mass of an electron, 9.110 times 10 to the negative 31 kilograms, and then times our coulombic charge on an electron, 1.602 times 10 to the minus 19th coulombs squared. Okay, before we do what the answer is, it's a good idea to check to see, do our units work out? Now we got newtons and we got joules, and so what I'm going to do is I'm going to bring everything back into the base SI units, right? Coulombs is a base SI unit, so a newton is kilogram meter second squared. A joule is a kilogram meter squared second squared. So if we take a look at all of our units, we'll do that right here. We have Coulomb squared. This is 1 over Newton, so we can take our unit, flip it. That gets seconds squared kilograms meters. Right, that's our Newton. 1 over meters squared for this one. Times up top the joule, so that's kilograms times seconds. This is squared, so that's kilograms squared, second squared. Down on the bottom, we have kilograms, and then we have coulombs squared. Okay, so R is radius. What units should a radius have? Meter, right? It's a distance. So all of our units should cancel out, giving us just meters at the end.
Wait, how did joule second simplify to become kg squared S squared? Because joules is kg.
You're right. Meters to the fourth, seconds, squared, so seconds to the fourth, seconds squared. Bonus point. Yeah, this is why keeping track of stuff is important. Okay. So, seconds, well, let's do the easiest one, the coulombs first, right? Though Coulomb squared cancels out Coulomb squared. Let's do kilograms next. Kilograms would be in the denominator. It's in the denominator, numerator. So these two sets are going to cancel out that one. We have seconds in the numerator, or second squared in the numerator, second squared in the numerator, seconds to the fourth in the denominator, so those will cancel each other out. And then we have meters in the denominator, meters squared in the denominator, and then meters to the fourth power in the numerator, and so that will cancel out, giving us meters in the end, right? So we're left with just that one unit. Okay, so what that tells us is, we might have made a mistake, but our units are right. So the likelihood that we made a mistake somewhere in the derivation reduces greatly if your units work out. So plugging those numbers in, you get 5.29 times 10 to the minus 11th meters, which we could express as 52.9 picometers, or 0.529 angstroms. All right, the actual distance for a hydrogen atom is about 0.5-ish angstroms. So that actually works out well. This is called the Bohr radius. That's the Bohr radius for a hydrogen atom. Not a hydrogen molecule, hydrogen atom, because we only worked out one of them. Okay. Okay, so we figured out the radius. What would be nice is if we could figure out the energy. Right, the energy of each one of those states, essentially because this equation here is sort of based on the energy. Right, so if we want to figure out how we get the Rydberg equation, 1 over the wavelength is directly proportional to energy. So if we could figure out the energy of two different states, we might actually be able to approximate this thing. Right? So up till here, this is working out the radius. The next part is figuring out the total energy of having the electron in that location. Okay. Okay, so our energy of a particular state, or our total energy, right, would be equal to the energy that's stored kinetically plus the energy that's stored in potential. The potential energy is based on the Coulombic attraction between the two charges, right? So holding the electron at this particular distance, that is where we're storing our potential energy. Right? We could have the electron move closer to the nucleus, in which case your energy would, some of that potential energy would decrease, getting converted into kinetic. Right? So our potential energy is our Coulombic force, which is minus CE squared over 4 pi permissivity 0 times R that's potential energy as a function of distance. Right? It's not the force, it's force times distance. Right? So the energy is the force times the distance. That's why this is R and not R squared. It's because if you take the force times the distance would be a radius, and so the two radiuses cancel out, leaving you that.
Why do you get a negative charge E squared now?
Because we're because of how we're defining the distance. As it comes closer and closer together, the energy goes down. Okay, going back to our kinetic was 1/2 mass times velocity. One half the mass of the electron times the velocity squared. And we had worked out right here, right? We have something that looks like that. So we can actually replace this with another expression that looks very similar to this, right? So using this relationship here that we developed before, we can replace the kinetic energy with something that has more similar units or similar values to our potential energy. So this would be equal to 1/2 M-E, no, replacing this with that. So this one has, if you compare this expression here, this is the one we had before times radius. Right, so if we take that side times radius, we end up with CE over 4 times pi permissivity times R, not R squared.
C's.
Squared. Another bonus. I think that's 3. Okay, and then this would be minus the potential energy. So that would be CE squared over 4 pi permissivity R. Right? Okay. So this is essentially 8 pi, or over 8 pi here, over 4 pi. You subtract the 2, you get, well, this would enable you to have similar denominators. This would be 2, or this one's twice the size of that one. So what we'd be left with when we subtract them is 1/8. C charge of electron squared over 8 pi E naught R. Okay, so if we're looking at, this is the total energy at a particular level. So a more common way to refer to this is the E at a particular N value. Right, so we want to look at an energy of the electron in the N equals 1 state. So those would be energy of any level, right, or the 1 state if we're interested in it, would be equal, oh, negative charge on electron squared over 8 pi E naught. We have R here, but I'm going to replace R with what we had before, this one here. Right, because this R value has our N in it, right, which will give us an equation to figure out the energy at any level, not just at N equals 1. So this is 4 pi E naught N squared. Instead of using my H bar, I'm going to use the H over 2 pi. The reason I'm doing that is I got a bunch of pi's here that I want to cancel out. So H over 2 pi squared divided by the mass of electron, charge on the electron squared. Okay. So I have H over 2 pi squared. If I pull the 2 pi out, right, after squaring that, that's 4 pi squared. That will cancel out this 2 once we square it, we'll cancel out the 4. And then this pi would be pi squared. This pi will cancel out the other 2 pi's. Right, so that's why in here, we're not going to see any pi. So this would be equal. Okay, we have the charge on the electron, which is in the denominator of the denominator, and so that goes up top. So this would be minus mass of the electron, charge on the electron squared times squared would be to the 4th power divided by, making sure I get this right, 8 E naught. We have the permissivity here times, it's also in that set of parentheses, so this would be permissivity squared. And then we got the H squared, and then I'm going to move the 1 over n out by itself to sort of highlight it as being the variable. Right, so everything here, these are all constants, right? That is a variable, because if we want to vary which energy level we're trying to figure out, it's the n is the variable, right? So I pulled it out for that particular reason. Space. We don't need a whole lot. Okay. So delta E would be the difference between 2 energy levels. So delta E would be equal to E some value 2 minus the E of some other n. Right? This is going to be equal to minus C minus mass of electron, charge of electron to the 4th power over 8 permissivity squared H squared 1 over n 2 minus that whole same thing again, okay, now, this whole thing here is the same on both sides, so we can pull it out, giving us our delta E is equal to minus m mass of the electron, charge on the electron to the 4th power over 8 permissivity, or permittivity squared H squared times 1 over n2 squared minus 1 over n1 squared. We're getting something that's looking a lot like this, but this is n2 squared and 1 squared, and we got a negative sign. If we take what's in the parentheses and flip them, putting the n1 first, that would be the negative of what we had before. That negative will cancel out that negative. So we can rewrite this as delta E is equal mass of the electron, charge of the electron to the 4th power over 8 permittivity squared H squared 1 over, that should be an n1 squared minus 1 over n2 squared. Okay, now, when we're talking about the energy, that's the energy contained, the thing that causes the electron to move to different energy level is the absorption of a photon, right? So that value, that energy, would be equal H nu. If we do the Rydberg thing, but in terms of 1 over wavelength, our relationship between wavelength and frequency is reciprocal. So if we have h nu, this would be equal to hc over lambda. If we want it just 1 over lambda, we gotta divide both sides by hc. That
How did you get H nu? How did you get H nu?
That's the energy of the photon that causes the electron to get kicked to the next energy level.
That was from last class, right? That was from last class?
Planck's constant. Yeah.
H nu of that.
That's frequency. Right, so one of the things where the Rydberg equation comes from is the photons that are coming off as the electron relaxes or gets excited or relaxes down from different energy levels and kicks off the photon. So how we're measuring N1 and N2, using this Rydberg equation is based on the photon that comes off. So the change in energy between those two energy levels comes off as the photon, and the photons have energy h nu. Okay? So if we move the h and the c to the underside here, right, to get our 1 over wavelength, I guess I can grab some, keep your notes from where you were. I'm just going to use this space here. More important space. Okay, so we're going to continue right here with what it finally looks like. I'm going to divide both sides by hc, right, to get my 1 over wavelength. So 1 over wavelength is equal mass of the electron, charge of the electron to the 4th power, divided by 8 permittivity constant squared h. I'm dividing it by hc, so this will be h to the 3rd times the speed of light, 1 over n1 squared minus 1 over n2 squared. So the Rydberg constant should be that number, right? If we plug in everything, and we will save that, I'll just tell you what the answer is if we plug in all that. Using this as the Rydberg constant, our RH from this is equal to 1.09737 times 10 to the 7th meters minus 1. That is within 0.5% of the experimentally determined value. So the experimental value, so this one here is theoretical. The experimentally determined one is 1.09678 times 10 to the 7th meters minus 1. Now, we're going to do one better in a sec, but we're going to pause here, let you guys soak up the glory of this, and take a break.